Have you ever looked up at the night sky and wondered, where did it all begin? The universe, in all its vastness and splendor, presents us with one of the most profound mysteries, its own origin. How did this immense tapestry of stars, galaxies, and cosmic wonders come to be? It's a question that has captivated humanity for millennia. The quest to understand our cosmic origins is a journey into the very essence of existence. It's about piecing together the story of our universe from the tiniest fraction of a second after its birth to the intricate web of cosmic structures we observe today. We'll delve into the Big Bang, the event that marked the birth of space and time as we know it. What is dark matter, this elusive substance that holds galaxies together? What drives the accelerating expansion of the universe, this mysterious force we call dark energy? Our exploration of the universe's origins is a journey through time and space, a quest to understand the grand narrative of our cosmic evolution. We'll begin our journey by examining the evidence for the Big Bang, the event that set our universe in motion. We'll explore the cosmic microwave background radiation, the faint afterglow of the Big Bang that still permeates the universe. From there, we'll trace the expansion and cooling of the universe, a process that allowed matter to coalesce and form the first stars and galaxies. We'll witness the birth of stars in fiery clouds of gas and dust, their nuclear furnaces forging the elements that make up our world and ourselves. Throughout our journey, we'll encounter some of the most fascinating and enigmatic objects in the universe: black holes, neutron stars, quasars, and more. As we embark on this cosmic adventure, it's important to remember our place within this grand scheme. We live on a small, rocky planet orbiting an average star, one of billions in the Milky Way galaxy, itself one of billions of galaxies in the observable universe. Our cosmic address is a humbling reminder of our place in the vastness of space and time. Yet, our insignificance in the grand scheme of things does not diminish the significance of our quest, for we are a product of this universe, forged from the same stardust that makes up everything around us. Understanding the universe's origins is, in a very real sense, understanding our own origins. Our journey begins with the Big Bang, the event that marks the birth of our universe. Picture this: 13.8 billion years ago, all of space, time, matter, and energy were compressed into an incredibly tiny, hot, and dense point known as a singularity. Then, in an instant, something remarkable happened. The universe began to expand. This wasn't an explosion in the traditional sense, like a bomb going off in pre-existing space. Instead, it was the expansion of space itself. Imagine a tiny balloon with dots drawn on it. As you inflate the balloon, the dots move apart from each other, just like galaxies in our expanding universe. Despite the mystery surrounding its cause, the Big Bang theory is supported by a wealth of observational evidence. By studying this evidence, scientists have been able to piece together a remarkably detailed picture of the universe's earliest moments. Section 2. Echoes from the Past. The cosmic microwave background. One of the most compelling pieces of evidence for the Big Bang is the cosmic microwave background radiation, or CMB. This radiation was discovered in 1965 by Arno Penzias and Robert Wilson, who initially thought it was interference from their antenna. What they had stumbled upon was a faint uniform glow coming from every direction in the sky. This glow, the CMB, represents the oldest light we can observe, a snapshot of the universe when it was young, hot, and dense. These wrinkles hold the seeds of the large-scale structures we observe today, the galaxies, clusters, and superclusters that make up the cosmic web. Section 3. Hubble's revelation, a universe in motion. For centuries, humans believed in a static, unchanging universe. However, in 1929, Edwin Hubble revolutionized our understanding of the cosmos with a groundbreaking discovery. The universe is expanding. Hubble observed that galaxies are moving away from us, and the farther away they are, the faster they're receding. Imagine baking a loaf of raisin bread. As the bread rises, the raisins, representing galaxies, move farther apart from each other. Hubble's observations, based on the redshift of light from distant galaxies, provided the first concrete evidence for an expanding universe. This realization fundamentally changed our understanding of the universe and our place within it. Section 4. The inflationary epoch. A universe expanding faster than light. While the Big Bang theory successfully explains many observed features of the universe, it also presents some puzzles. One of these is the horizon problem. Why is the universe so remarkably uniform on large scales? To address this and other cosmological conundrums, physicists proposed the theory of cosmic inflation. This theory suggests that in the first fraction of a second after the Big Bang, the universe underwent a period of incredibly rapid expansion, growing exponentially in size. While still a theory, cosmic inflation has gained significant support from observations, particularly the detailed measurements of the cosmic microwave background radiation. The universe, far from being a static and unchanging stage, is a dynamic and ever-evolving entity. One of the most profound discoveries in the history of astronomy was Edwin Hubble's observation that the universe is expanding. Imagine a loaf of raisin bread dough rising in the oven. As the dough expands, the raisins, representing galaxies, move farther apart from each other. Similarly, the expansion of the universe causes galaxies to move away from each other. This expansion isn't like an explosion, where objects are propelled outward through pre-existing space. Instead, it's the very fabric of space itself that is stretching. The expansion of the universe has profound implications for our understanding of its past, present, and future. Observational evidence for the expansion of the universe comes from a variety of sources, including the redshift of light from distant galaxies, the cosmic microwave background radiation, and the observed abundance of light elements. Edwin Hubble's groundbreaking discovery wasn't just that the universe is expanding, but that there's a direct relationship between a galaxy's distance from us and its recession velocity, the speed at which it's moving away from us. This relationship, now known as Hubble's law, states that the farther away a galaxy is, the faster it's receding from us. Imagine you're standing on a sidewalk, watching cars drive away from you down a straight road. The cars closer to you appear to be moving slower, while the cars farther away appear to be moving faster. Hubble's law works in a similar way, but instead of cars, we're talking about galaxies, and instead of a road, we're talking about the vast expanse of space. The slope of this line is known as the Hubble constant, denoted by h0, and it represents the rate of expansion of the universe. Resolving this tension is crucial for refining our understanding of the universe's expansion history and could provide insights into the nature of dark energy. It's important to emphasize that the expansion of the universe is not simply galaxies flying apart through space like shrapnel from an explosion. Instead, it's the very fabric of space itself that is expanding, carrying galaxies along with it. Imagine drawing two dots on a balloon and then inflating it. As the balloon expands, the dots move farther apart, not because they're moving across the surface of the balloon, but because the balloon itself is stretching. Similarly, The expansion of the universe is a stretching of space-time, the fabric of the cosmos. This stretching of space-time has some intriguing consequences. For example, it means that the light from distant galaxies is stretched as it travels through the expanding universe, causing its wavelength to increase. The expansion of space-time also has implications for the future of the universe. If the expansion continues to accelerate, as current observations suggest, it could eventually lead to a scenario known as the Big Rip, where the very fabric of space-time is torn apart. The concept of an expanding universe often leads to a perplexing question. If the universe is expanding, what is it expanding into? The universe is everything, all of space, time, matter, and energy. There is no outside for it to expand into. Instead, the expansion represents the creation of new space throughout the universe. The expansion of the universe is a mind-bending concept that challenges our everyday intuitions about space and time. The Big Bang Theory, with its elegant explanation of the universe's expansion, faced a perplexing puzzle, the horizon problem. This problem arises from the observed uniformity of the cosmic microwave background radiation, CMB. Imagine looking at 2 points in the sky on opposite sides of the Earth. These points are separated by vast distances, billions of light-years apart. Despite their lack of communication, these distant regions exhibit remarkably similar temperatures in the CMB. The horizon problem challenged the standard Big Bang model, suggesting something was missing from our understanding. To address the horizon problem, physicists proposed cosmic inflation. In the early 1980s, the universe underwent rapid, exponential expansion. Imagine a tiny region inflating to a size larger than our observable universe. That's cosmic inflation. The universe expanded faster than light, solving the horizon problem. The inflaton field drove this expansion. Like a ball rolling down a hill, it released energy, driving expansion. This smoothed out initial variations, explaining the CMB's homogeneity. Inflation smoothed the universe, but left tiny density and temperature variations, seeds of structure formation. These variations, amplified by gravity, formed galaxies, clusters, and the cosmic web. The cosmic microwave background reveals these primordial fluctuations. Tiny CMB temperature variations, measured by WMAP and Planck, show early universe density regions. Imagine a still pond with ripples, like density variations in the early universe. Ripples reflect disturbances, like CMB temperature fluctuations reflect early density variations. These density variations, from inflation, acted as gravitational seeds. Higher density regions attracted matter, forming stars, galaxies, and cosmic structures. In the immediate aftermath of the Big Bang, the universe was an unimaginably hot and dense soup of energy. The universe was teeming with a chaotic sea of fundamental particles, quarks, leptons, and bosons. Quarks come in 6 flavors: up, down, charm, strange, top, and bottom. Leptons include the electron, muon, tau, and their neutrinos. Bosons mediate the fundamental forces of nature. As the universe expanded and cooled, these particles formed matter. As the universe expanded and cooled, the strong force began to dominate. This force binds quarks to form hadrons. As the universe cooled, quarks combined to form stable hadrons. Protons and neutrons are the most familiar hadrons. Protons have 2 up quarks and 1 down quark. Neutrons have 1 up quark and 2 down quarks. The strong force ensures their stability. Section 3. From plasma to atoms. The universe cools and simplifies. For the first 380,000 years after the Big Bang, the universe was a hot, dense, and opaque plasma. Temperatures were so extreme that electrons couldn't bind to protons and neutrons. Instead, they existed as free particles, constantly colliding with photons. As the universe expanded and cooled, recombination occurred. Electrons were captured by atomic nuclei, forming neutral atoms. Photons were free to travel unimpeded, making the universe transparent. This light is what we observe today as the cosmic microwave background radiation. Stars in the outer regions of spiral galaxies orbit much faster than expected. This speed suggests more gravitational pull than visible matter provides. Imagine swinging a ball on a string. Faster swings mean more tension, like stars needing more gravity. This led to the theory of dark matter, unseen but influential. The galaxy rotation problem and gravitational lensing provide compelling evidence for dark matter. This invisible substance makes up a significant portion of the universe's mass energy. We infer dark matter's presence through its gravitational effects. It shapes the motions of stars, the bending of light, and cosmic structures. Unraveling the universe's hidden sector. The quest to identify dark matter is one of the most exciting frontiers in modern physics. Scientists use direct detection, indirect detection, and collider searches to unlock its secrets. Direct detection experiments aim to detect the faint recoil of atomic nuclei when struck by dark matter. Imagine dark matter as a bowling ball colliding with a pin, an atomic nucleus. The recoil would be a telltale sign of dark matter's presence. Indirect detection searches for annihilation or decay products like gamma rays or neutrinos. Collider searches aim to produce dark matter particles by smashing protons together. If created, dark matter particles would interact weakly, inferred by missing energy in collisions. The search for dark matter is challenging but rewarding, bringing us closer to understanding the universe. In the late 1990s, astronomers discovered the universe's expansion is accelerating. Observations of distant supernovae revealed this mystery, introducing dark energy. Imagine a car on a highway. You'd expect it to slow down. Similarly, the universe should slow due to gravity. But type Ia supernovae showed the universe is speeding up. They were farther away than expected. This indicated the universe's expansion is accelerating. It's like a car accelerating instead of slowing down. To explain the universe's accelerated expansion, scientists invoked dark energy, a mysterious force making up 68% of the universe's energy density. Unlike gravity, dark energy acts as a repulsive force, driving the universe's accelerated expansion. Imagine a balloon with dots representing galaxies. As the balloon inflates, the dots move apart. This is analogous to dark energy stretching space-time. The exact nature of dark energy remains a major mystery in physics. If dark energy continues to dominate, galaxies will become increasingly isolated. Unraveling dark energy is a top priority for cosmologists and astrophysicists. Scientists employ observational and theoretical approaches to measure its properties. Studying the universe's expansion history and distant supernovae, mapping galaxy distribution, and studying cosmic microwave background radiation helps reconstruct the universe's expansion rate. Another approach studies the growth of cosmic structures. Dark energy's repulsive force influences these structures. Observing structure growth over time reveals dark energy's properties. Theoretical physicists develop models to explain dark energy. These models range from modifications to Einstein's theory to new fundamental fields or particles. Each breakthrough brings us closer to understanding this mysterious force. The universe's vast structure began with minute quantum fluctuations during the inflationary epoch. These tiny variations served as seeds for galaxies as the universe expanded and cooled. Higher density regions attracted more matter, forming gas clouds and initiating star formation. This process continued, transforming gas clouds into the first galaxies. Supernova explosions enriched the gas with heavier elements, paving the way for new stars. Early stars and galaxies illuminated the universe, ending the cosmic dark ages. These galaxies began to merge and interact, shaping the diverse galaxy types we see today. Dark matter, making up 27% of the universe's mass, is crucial for galaxy formation. Its gravitational effects help us understand how galaxies form and cluster. In the early universe, dark matter provided the scaffolding for visible matter to form galaxies. Higher concentrations of dark matter created gravitational wells, attracting gas and other matter. These halos served as gravitational anchors, allowing galaxies to form and stay bound. Simulations like the Millennium simulation show dark matter's role in shaping cosmic structures. Dark matter halos grow, merge, and interact to form larger structures. Visible galaxies are bright beacons within vast invisible dark matter halos. Dark matter's role extends to forming galaxy clusters and superclusters. These structures are held together by dark matter's gravitational pull. Observations, especially through gravitational lensing, provide evidence for dark matter. Understanding dark matter is key to unraveling galaxy formation and cosmic evolution. Ongoing research continues to shed light on dark matter's role in shaping the universe. The large-scale structure of the universe is often described as a cosmic web, a vast network of galaxies and dark matter interconnected by filaments and separated by immense voids. Galaxies are found within clusters and superclusters, connected by vast filaments of dark matter and intergalactic gas. Galaxy clusters are located at the nodes where filaments intersect. The regions between these filaments, known as voids, are sparsely populated with galaxies. The formation of the cosmic web began with the initial density fluctuations in the early universe. As these fluctuations grew under the influence of gravity, matter began to flow along the paths of least resistance. The interplay between gravity, dark matter, and dark energy has shaped this intricate web. Observing and mapping the cosmic web is a major focus of modern cosmology. Large-scale surveys, such as the Sloan Digital Sky Survey and the Dark Energy Survey, have provided detailed maps of the distribution of galaxies and helped to reveal the underlying structure of the cosmic web. Black holes, those enigmatic objects from which not even light can escape, play a crucial role in the evolution of galaxies. They form when massive stars exhaust their nuclear fuel and collapse under their own gravity. This collapse triggers a supernova, a cataclysmic explosion that can outshine an entire galaxy. The core continues to collapse, creating a region where the escape velocity exceeds the speed of light. This region is a black hole, a point in space-time where gravity is so strong that nothing can escape. While stellar mass black holes are impressive, they pale in comparison to supermassive black holes at galaxy centers. These giants can be millions or billions of times more massive than our Sun. Their influence on galaxies is profound. Imagine an event horizon encompassing our entire solar system. They grow over billions of years, accreting matter and merging with other black holes. Gas and dust form an accretion disk heated to incredible temperatures. This emits intense radiation across the electromagnetic spectrum, making active galactic nuclei some of the most luminous objects in the universe. Quasars and active galactic nuclei, beacons of the early universe. Supermassive black holes powered the most luminous objects ever observed. Quasars. Imagine a beacon shining across billions of light years, outshining stars. Quasars represent an early stage in galaxy evolution. They release tremendous energy, illuminating the early universe. The Big Bang theory explains the universe's expansion, the cosmic microwave background radiation, and the abundance of light elements. It is the prevailing model in cosmology. However, scientists explore alternative theories, seeking a more complete understanding of the universe. Science thrives on questioning and pushing boundaries. New discoveries might challenge our current understanding. Alternative models propose different mechanisms for the universe's origin. Some suggest a universe that has always existed. Others propose modifications to Einstein's theory. These theories challenge us to think creatively and critically. We must remain open to new ideas as we explore the cosmos. The steady-state theory, proposed by Sir Fred Hoyle, Thomas Gold, and Hermann Bondi, suggested a universe infinite in extent and eternal in duration. It envisioned an expanding universe with a constant average density over time. This required the continuous creation of matter at a very slow rate. However, the discovery of cosmic microwave background radiation supported a universe with a finite age and a hot, dense beginning. The steady-state theory, though no longer viable, was crucial in the development of cosmology. Perhaps one of the most intriguing concepts in modern cosmology is the idea of a multiverse, a collection of multiple universes, each with its own unique properties and laws of physics. While still speculative, the multiverse hypothesis has gained traction among some physicists and cosmologists. Imagine a vast cosmic landscape filled with bubbles of varying sizes, each representing a different universe. Some bubbles might be similar to our own, with galaxies, stars, and planets, while others might be radically different, governed by entirely different laws of physics. The multiverse hypothesis arises from various theoretical frameworks, including eternal inflation, string theory, and quantum mechanics. Eternal inflation suggests our universe is just one bubble in a vast, ever-expanding multiverse. New universes are constantly being born through quantum fluctuations. String theory allows for multiple universes within higher dimensions, each with its own unique configuration of strings and brains. While intriguing, the multiverse hypothesis is highly controversial and difficult to test directly. Some argue that the fine-tuning of our universe's physical constants might be explained by the existence of a vast multiverse. The concept of a multiverse pushes the boundaries of our imagination and challenges us to rethink our place in the cosmos. It raises profound philosophical questions about the nature of reality, the uniqueness of our universe, and the possibility of other universes, perhaps teeming with life, existing beyond our own. As we peer into the distant future of the universe, we encounter a cosmic tug-of-war between gravity and dark energy, the mysterious force driving the accelerated expansion. The outcome will determine the ultimate fate of the cosmos. Currently, dark energy is winning, causing the expansion to accelerate. Observations of distant supernovae and the cosmic microwave background all point to this accelerating expansion. However, the future remains uncertain. The properties of dark energy will ultimately determine the universe's fate. If dark energy continues to dominate the universe's expansion, the cosmos will slowly fade into darkness, a scenario known as the Big Freeze. Galaxies will drift farther apart, and the universe will cool, approaching absolute zero. Stars will exhaust their fuel and fade, leaving behind remnants like white dwarfs and black holes. Eventually, even these will evaporate, leaving an empty, cold universe. It's a bleak end, a slow fade into darkness. While the Big Freeze is considered the most likely fate of the universe, other scenarios are possible. Two such alternatives are the Big Rip and the Big Crunch. The Big Rip envisions dark energy tearing apart galaxies, stars, and even atoms. The Big Crunch represents a reversal of expansion, with the universe collapsing in on itself. Galaxies would collide and merge, leading to extreme density and temperature. This raises the possibility of a cyclical universe, with a new cycle of expansion and contraction. From the Big Bang's fiery birth to the intricate dance of galaxies, it's humbling to reflect on our place in this grand cosmic tapestry. We are a product of this universe, our existence intertwined with events billions of years ago. The atoms in our bodies were forged in stars, scattered by supernovae, and drawn together by gravity to form our planet. We are, as Carl Sagan said, star stuff, a testament to the universe's ability to create complexity and beauty. Our exploration of the universe is far from over. Many mysteries remain, challenging us to push the boundaries of human knowledge. What is the true nature of dark matter and dark energy? How did the first stars and galaxies form? Are there other universes out there? These questions drive cosmologists to explore the cosmos. Each new observation brings us closer to unraveling the universe's secrets. The pursuit of knowledge is an ongoing journey. As we delve deeper into the universe's mysteries, we encounter a sense of wonder and awe that transcends the boundaries of science. The vastness of space inspires humility, connecting us with something profound. It's about appreciating the beauty of the cosmos and the possibility of life elsewhere. The study of the universe offers perspective, reminding us of our interconnectedness. So, the next time you gaze up at a star-filled night sky, let the universe's grandeur inspire